All right, so this is a quick overview of a C file that I wrote for our Games for Geeks class. And I'm going to share my screen so you can see it. So here is my screen. And this is the file here, run. So I'm going to show you the C file here. And basically this is a nearest neighbor simulation file, a starting point for what we're talking about in class. So let me show you really quick what it does. The first thing it does is it spits out a bunch of these graphs. And let me just show you what those are. So the twos are basically boundaries. So you notice there's a boundary all around the whole thing. And then there's a boundary here in the middle. There's sort of a wall with a little door in the middle. You punched out a little hole. The ones are particles, and they move around. So we evolve this one step, and things start to move around. And then as we keep running the steps, it keeps moving around. And eventually, they start going through the door here and ending up down in the lower section. And if you keep running it, eventually most of them are in the lower section. And if you keep running, some of them might come back through, but on average they stay in the bottom section. And the reason for that is in the code. So there are two arrays, an AX array and an AY array. And A doesn't really mean anything, I just picked a letter. And you notice that there's 10 of each of a -1, 0, and a 1 on the AX, but there's a little different. There's more ones on the AY. And what that means is if we randomly choose an element from this array, we're twice as likely to get a 1 as we are to get a 0 or to get a -1. That gives it a slight pressure in quotes, to go from the top to the bottom in our setup. So the program starts by, we create this grid. We start by just putting, zeros in it here. And then we add those boundaries, the twos. And then we create a little wall in the middle here. And then we punch a hole right in the middle of the wall right there. And then we add pieces that move around. That's the ones that are in there. And then we print that thing out so we can see it. This function here just gives us a random move because remember there's a nearest neighbor thing where you have 9 squares, and the middle one is the thing that's moving or being checked, and all the other 8 squares around it are basically influencing that one square. So this other function here is the nearest neighbor processing, and we basically copy the nearest neighbor graph from the main graph and then do things to it. And the things we do to it are checked if it's a value of 1, 0, -1, or 2, and then do different things based on that. You can look at that. And then we put that nearest neighbor graph back into the main graph once we're done. And then this right here, this function move graph, just goes through and checks for ones. Whenever you get a 1, it processes the nearest neighbors for that 1 and allows it to move in other things. The main here just runs this 100 times. It starts with the initialization of the graph. It does a move graph. And then you need this one right here, the ABS graph, because basically in order to tell whether a piece is moved or not, we change it from a 1 to a -1. And so if it's a -1, it's been moved in this particular iteration. And so then in order to get all ones again, we take the absolute value of everything in the graph, and then we print it off, and then we repeat it again. And essentially, we can do things like we could change the size of the graph. So let's say, for instance, here we wanted to go 9 wide by 13 tall. We'll save that and come over here, and we have to compile it first here, and then we run it. Notice it changed to 9 wide by 13 tall, and it's a whole lot longer now. Let's see. There we go. And it starts off, I put all the ones all the way in the opposite side to begin with, but you can put them at other places. And there's just one hole right there in the middle. And then they start moving around as the graph starts going through in each iteration. And eventually, as you go through, the pieces begin to end up in the bottom after a while. Here's one. You keep going, and they end up in the bottom. And keep going. Here we're in 79, and we're about half and half. And here at 92, all but well, there's still 3 wandering around up in the top. So if we want to increase the pressure for getting things down in the bottom, we could do this. For instance, we could take the -1 pressure that pushes it back up, and we could delete all of these. And we'll save that. So now we have a much higher pressure. We have 10 times, 20 times more likelihood to go down than up. And we'll compile that again and run it. And this time you'll notice at the end, all of them are sitting at the bottom here. And so let's see how long. I don't know, they're all on the bottom at 66. They're all on the bottom at 34, 12, 13, 15, 16, 18. There's still some in at 20, 23, 25. The last one seems to be going through right here, and now it's down below. And I think from there on, from 25 down, they're all in the bottom. So we basically increase the pressure for it to move down. And you can just go play with this and see how it works. Check the graphs, watch it, change the parameters. I just thought that would be a good starting point for you guys for this nearest neighbor simulation. So that is it for today.